Hi guys, Sajjad Hussain again. This is the second part of my building design video. In the first part, I introduced the geometry of the building and I explained to you that I took this example from PCA notes of 31808. The example number was 29.1, design of a 12-story cast-in-place frame shear wall building and its component. The information is provided over here that concrete strength is 4000 psi, reinforcement is 60 ksi, loads are also defined over here. And why I selected this example, as I explained, that this building is assigned to seismic design category D, is a dual system. That means in north-south direction it is a special reinforced structure with the special moment frame, and in east and west it is a special moment frame. So this was the model. We have almost completed the geometry. Couple of things were remaining, so let us define that one. For example, as I explained, that if you go step by step in the model explorer, you will see that the tree shows the step, and we can follow this step by step tree. So we have already defined the material, we have already defined the frame section, slab section, wall, like wall 5 and wall 6, these are already defined. Now we have to define one more thing, that is we have to assign the piers to these walls. Let's go to the elevation B. Here we have to assign piers to these wall sections. Now we can define the piers. So pier number 1, 2, 3, we can add couple of more piers, or it's okay, we can assign these pier definitions to these shear walls. So let's select the mid wall, and we can assign shell pier level pier 1, and pier 2 is there because they have similar conditions. Similarly, we can select the elevation of elevation G. All are pier 3. So we can change this pier to pier 1 type. Assign shell pier 1, apply. So having defined assigning the piers, let's go to 3D model. Now we can select the slabs. All floors we can select, and we can assign the diaphragm. D1 is the rigid diaphragm, so we can assign them as rigid diaphragm. So now the geometry is complete. Now we can switch to loads. Here if we see two load patterns are already defined, that means the dead load and live load, these are already defined. So we have to define seismic, that means let's define earthquake. This should be seismic and it should be as per ASCE 16. Similarly, we can define wind. This should be defined as wind as per ASCE 716. Now we have to modify these loads. We know that the earthquake load has to be modified. Now we can see that the direction and eccentricity. So all these 6 checkboxes are checked. That means it will define the seismic load in x direction. It will define with the plus eccentricity and minus eccentricity in x direction. Similarly, it will define the y direction and y direction plus minus eccentricity. And eccentricity is 0.05. That means 5% eccentricity. So that means this load case will generate 6 different load cases, 3 in x direction and 3 in y direction. Now it will calculate time period. We can define approximate or the program calculated. Let us leave for program calculated. And I have already defined these values over here. Now, as you can see that value of CT is 0.016 and its coefficient is 0.09. So let us select these values. CT is 0.016 and X is 0.9. So we have already defined these values. So now the program will calculate the time period for this structure. The story range is of course from base to the top story, which is 12. Now the values of SA and SS and S1. I have already defined these values or considered these values over here. The value of SS is 1.2295 and the value of S1 is 0.3708. These values are for Islamabad region. So let me input these values over here. 1.95. S1 is 0.3708. Long period you can calculate. You can leave this as it is. Sometimes maybe I change it to 12. So for the time being it's okay, 8 seconds. Site class, site class should be taken as D because this is as per definition of Building Code of Pakistan 2021 and its para is 1613.2.2. So let's select site class D. Importance factor as 1 and rest is okay. So site class is D. importance factor is 1. Now other factors like response modification R, system over strength omega, and deflection, let us check from where we can take these values. So as I have already compiled these values, these are FA and FV values. They are exactly matching with the ETABS calculated values. This is the response spectrum. Now, since this is a special reinforced, sorry, there was something wrong. I was disconnected, but anyway, it's restored now. And these values are for east-west. In north-south direction, as we know that this system is a dual frame system, so a special moment, a special reinforced concrete shear wall, then the value of omega should be, sorry, omega, the value of R should be 7, omega 2.5, and CD is 5.5. So let us take this value. R is 3, R is 8, omega naught is 3, and CD is 5.5. So when we input these values, that means the response factor is 8, omega 3, 5.5. So for the time being, it's okay. Now wind. The first choice is exposure and pressure coefficient. The exposure from extent of diaphragms, yes, this is a good option. We can select that one. Otherwise, if we say exposure from frame and shell objects, so we have to include the shell, etc. So let's leave that option and we can select the first option, which is exposure from extent of diaphragm. Wind pressure coefficients. We can leave for program determined. Wind direction and exposure width. Based on the diaphragm, already values are taken, so this is fine. Case, create all sets. What does it mean? So it will create 12 load cases. The complete set is given over here. That means it will consider first the angle 0, then 90, that means two perpendicular directions. Sorry. And all the load cases as per ASCE 7. These are conditions defined, so all these load cases are there. Eccentricity, okay, 0.15, leave it as it is. Wind speed, mile per hour. So for us, as per Building Code of Pakistan, the wind condition, it says that the basic wind velocity should be 100 miles per hour. Let's input this value. That means wind speed should be 100 mile. Exposure C, ground elevation factor 1, topographic factor KZT is 1, gust 0.85, directionality factor KD is 0.85. Exposure height, top story is the top 12th story and bottom is the base, that is okay. There is no parapet, so I am not including the parapet over here, no need to check this box. So all these parameters are defined. Okay, so all these loads are defined. But let's go to plan. So here we have to select only one story. Now we are going to assign loads. Assign shell load uniform. So we have to define the superimposed dead load as superimposed dead load for the roof is only 10 pound per square feet. So we will define 10 pound per square feet, and it should go to add to the existing loads. Okay, so the 10 pound per square feet load is assigned to the whole slab. We will go down further. Now we can select similar stories, and again assign shell load uniform, and now the shell load will be 30 pound per square feet. So here we are going to add 30 pound per square feet, and it is going to add to dead load, apply. Okay. Select floors. Okay, assign shell load uniform 30, apply. Okay, so let's check for the top. So roof, again, because we selected all, so roof is also selected, and we can modify now. We have to select only this story. Assign shell load uniform. Now it should be 10. Assign shell load uniform. No. Select floor. Okay. No. Select all. Assign shell load uniform, apply. Why something wrong. Anyway, for the time being we can leave it as it is because this is identical. So the dead loads are assigned. We can select again all floors, and now we can assign the live load. Live load, we know that the live load is 75 pound per square feet. So let us assign this value, 75 pound per square feet. Apply. Okay. So for the time being this is okay. Let's see the 3D model. Save the model over here. Now loads, we have to go to load combination. We can add default. The default load combination: concrete frame design, concrete shear wall design, and concrete slab design. Okay, so all the load combinations are added automatically. So this is complete load definition. Now we can check. Let's analyze. So this is the deformed shape. We can check by animation. Let's start the animation. Now you can see that the structure has properly moving in vertical direction for dead load case. You can see the dead load case. We can check another one. This is for live load case. This animation is very powerful tool. It shows the deflection and it gives the feel that the loads are defined in correct sense and in correct direction. Since the load is vertical, so all the movement is in vertical direction. Next, now earthquake load, this has generated, oh, something wrong. I'll check later, but let us stop over here. I will show all the animations in all the directions, and then in the next video I'll explain the output and design the structure. So for the time being, this is I think I should stop now. Okay, bye.